Okay, so today's lesson, it's our second last lesson for vectors. We are going to be looking at 9.4, the distance from a point to a line. So let's start with this wonderful drawing here, which I did not do. That's why it's wonderful. And this is 2 dimensions. So we're going to start with 2 dimensions. So in 2 dimensions, we have our xy plane. Then we have some line here. Notice that I wrote the line for an equation in Cartesian form, which I can do in 2 dimensions. I just can't do it in 3 dimensions. Then we have a point that exists somewhere outside of the line. And then we have a point that exists on the line. Now if we connect this point to the closest point on the line, which would be right here, that is where you would have a perpendicular angle here. So 90 degrees angle, because that would be the closest distance to the line. And we can extend that as just a vector P naught Q. And this would be P naught P1. Now therefore, there is some angle between P naught Q and P naught P1. So we just call it theta. It's also important to note that because this line, which is the distance to the closest distance to the line, is perpendicular to the line, it's parallel to the normal of that line. And we can easily grab the normal just from your coefficients here. AX, BY, so your normals A and B. So how are we going to do this? Well, technically what we want to do is figure out this distance here. That's the closest distance to the line. So we're going to start with the dot product. So we have P naught P1, so this here, dot the normal, which is parallel to this here, equals the magnitude of this times the magnitude of the normal times the cos of that angle. Now we can also look at this as just a right angle triangle, and we can use SOHCAHTOA to actually figure out what the cos of theta is as well. So here we have our second equation. So cos theta equals adjacent, which is right here. It's P naught R, which is what we want, divided by hypotenuse, which is right here, P naught R1. So that's what we have here. So what we're going to do is we're going to replace this cos theta in equation 1 with this ratio from equation 2. And when we do that, notice that immediately you will have this P naught P1 cancel with that. And then we can divide both sides by the magnitude of the normal to actually solve for P naught R, which is that distance that we want, the closest distance to the line. Okay, now P naught P1, well, if P naught has coordinates, which I've written up here as just x naught, y naught, and P1 has coordinates x1, y1, we can find out that vector just by finding the differences between those coordinates. And then we are going to dot it with the normal vector, which is just AB from here. And if we do that dot product, so right now I'm just trying to analyze the numerator here. If we do that dot product, we'll get A times by our x coordinate here, and B times by our y coordinate. And then we just expand and collect like terms. So this we have AX1 minus AX0, and the same with B. Now the denominator, the magnitude of the normal, you can just use our magnitude equation and do the square root of A squared plus B squared. Now a couple of things I want to point out. One, notice this right here, AX1 BY1. If we go up to the equation, this is the equation for our line. And if we plug in values for x and y for a point that is on the line, we can solve for C. And x1, y1 is a point that is on the line. Therefore, I can replace ax1 plus by1 with negative c. It's negative because we would bring this c over to the other side of the equation. Now we have negatives throughout here. And since we're looking for a distance, we care about a positive value. So we'll just factor out a -1 and take the absolute value of that. And this is our equation. Then to find the distance from a point to a line, very, very important, in 2 dimensions. This does not work in 3 dimensions. So let's do an example with this, and then we'll go to 3 dimensions later. 3 dimensions is over here, but we'll come back to that. Let's go over here to question 1, or example 1. And we're going to apply this formula, just to see how it works. There's my pen. All right, so here we have a line. Notice it's in Cartesian form. I can do that in 2 dimensions. So 5x minus 3y plus 15 equals 0. And here I have a point P, makes sense, minus 6 and 4. Now our equation, the distance between that point and the line, just writing the equation we just derived on the front of the handout. So ax naught plus by naught plus c all over the square root of a squared plus b squared. Okay, so what are these based on the given information we have here? Well, this is a. So this is from our, oh, I said A and I wrote B. Let me do that again. This is A, based on our standard form of a line. This is B, so that's a -3, and that's C. Okay, now x naught and y naught, right, is a point that's not on the line that we're looking for, and that's what these are. So that's x naught, and that's y naught. So I'm pretty much going to sub these into the equation and solve. So we end up with the magnitude of, so 5 times -6, right, for x naught, plus b, which is -3, times y naught, which is 4, plus c, which is 15. All divided by the square root of a squared, which is 5, so 5 squared, plus b squared, which is -3 squared. If you simplify that, you'll get, well, you get -27 in here on the numerator, but if we take the absolute value, we'll have positive 27 over the square root of 34, which is approximately 4.63 units. Right? And that's how we can use the equation to figure out the distance between a point and a line. So let's do example 2, and then we'll go to 3 dimensions. So example 2, it says calculate the distance between 2 parallel lines. Well, can't use the formula. The formula is for a point and a line. So what am I going to do here? Well, let's call this one line 1 and this one line 2. Now what we can do is we can find a point on line 2, okay? And then find the distance between that point and line 1. So to find a point on line 2, I guess the easiest thing is just say an intercept. So let's go with the y-intercept. So for the y-intercept, x is 0, and we'll get a -12 equals 60. Forgot the y there. And so y equals -5. So there we go. We have a point on the line now. That's 0 and -5. Okay, so now we have a point here on line 2, and we have line 1. So if I find the distance between line 1 and that point on line 2, I'll know the distance between those parallel lines. And that we can use our equation for. So d equals, so we have ax naught plus by naught plus c all over square root of a squared plus b squared. All right, so since the line we're using is line 1, there's our a coefficient, there's our b coefficient, and there's our c coefficient. And this is the point we're going to use, so that's x naught, and that's y naught. Since x naught is 0, that whole first term on the numerator is gone. So we're left with b, which is minus 12, times y naught, which is negative 5, plus c. Remember, you're using c from line 1, not line 2, so plus 60. All over the square root, kind of going over my allowed space here, all over the square root of a squared, so 5 squared plus b squared, negative 12. So 5 squared plus negative 12 squared. And that'll be equal to 120 over 13, which is approximately equal to 9.23. So now let's look at 3 dimensions. We can't use the same formula because we can't use a Cartesian equation for a line in 3 dimensions. We have to use the vector equation. So looking at this diagram, here we have a line. Now we have a direction vector, m, on that line. And we have some point q on the line. We also have some point p not on the line. Now the distance between p and the line, the shortest distance, again, still makes a right angle to the line. Okay, so what we can do then is if we connect q and p, right, into this vector, qp, and we have our directional vector for the line parallel to the line, m, we can find the cross product of it. Because we know those vectors are off by an angle theta. So we can write m cross qp equals the magnitude of m times the magnitude of qp times the sine of theta. Now I don't have any directional vector here, which is why I wrote that this is the magnitude of the cross product. Okay, we don't care about the direction here. And I can also write, because again, this is a right angle triangle, I can also write that the sine of theta is opposite over hypotenuse, or rearranging for opposite, we know that d would be the magnitude of the hypotenuse times sine of theta. And so I can replace this here, which is equal to d, right up here. Divide by the magnitude of m, and we get that distance d equals the magnitude of the cross product between m and qp divided by the magnitude of that direction vector. So this is how we can actually solve for distance between a point, the closest distance between a point and a line in 3 dimensions. So let's try an example to see how we would actually apply that. So in this example, you can see we're given a point on the line P and a line. And this line is in vector form because we can't have it in Cartesian form. All right, so there's 2 ways of doing this. Method 1 is using the formula that I showed you. So our formula is D equals M cross QP divided by the magnitude of M. Okay, so what are these? M is the direction vector for the line, so it's right there. That's M. 0, 1, 1. QP, I don't actually know QP, right? But I do know a point on the line right here, and I do know a point off the line, and that's what QP actually is. If you go back to that diagram, QP goes from a point on the line to a point off the line. So I can figure out what QP is then just by taking the difference in their coordinates. So it would be -1. So -1 subtract, sorry, 1, not this one. That's the point. -1 subtract 1. 1 minus 2. And 6 minus -1. Right? So essentially this is our point Q here. So this gives us QP as -2, -1, and 7. So now I can do the cross product. Let's first do the cross product. So M is 0, 1, 1. And we're going to cross that with QP, which is -2, -1, and 7. All divided by the magnitude of M, which is the square root of 0 squared plus 1 squared plus 1 squared, which is just √2. All right, so let's do the cross product. We've done this many times before. Go watch the video if you need a refresher. Okay, we're going to have 7 subtract -1, -2 minus 0, and 0 minus -2. All divided. Yep. Oh, the square, like here. I'll do it over here. So the magnitude of M, it's just using our magnitude equation, right? We take the square root of 0 squared plus 1 squared plus 1 squared, right? Which is just 0 plus 1 plus 1, or √2. Okay. Now we're just going to simplify this a bit. So we get 8, -2, and +2. And we still have to find the magnitude of that, which would be the square root of 8 squared plus -2 squared plus 2 squared all over √2, right? Which actually leads to, let's see, 64 plus another 8, so √72, which would be divided by 2, √36, which is just 6. Okay, now that's one way of solving that problem. I'm going to show you another way of solving it. And this other method of solving it, it's a little more work, but it has an extra advantage as you can actually find the coordinate of the point on the line that the point you're looking for is closest to. Let's go over method 2. I'll use this space here as well. So method 2. So I'm going to rewrite what we have up there. So our line is 1, 2, -1, plus t, 0, 1, and 1. And the point is -1, 1, and 6. Okay, so how do I find the distance between this line and that point? Method 2. So first, change our vector equation into parametric form. So we get x equals 1, y equals 2 plus t, and z equals -1 plus t. All right, now what I'm going to do is, here we have a point P. We need a point on the line, right? This is similar to what we did up there, but I can't just pick a point on the line. What I'm going to do is I need the closest point on the line. So what I need, if I go back to this diagram, I can show you. I need this point R. That's the point I need. Now I can't really figure out what R is, but what I can do is simply say that R is the point X, Y, which is 2 plus T, and Z, which is minus 1 plus T. There we go. I just don't know what T is, but that's what R is going to be. And therefore, I can solve for RP, which is the distance we're looking for. If I go back to this diagram here, if I solve for RP, that's the shortest distance that we're looking for. All right, so let's figure out what RP is then. RP is just going to be, now we're just taking the difference between the coordinates of R and P. So we're going to get minus 1, minus 1, 1, subtract 2 plus T, and 6, subtract negative 1 plus T. All right, so I can just clean that up a little bit. We get negative 2, 1 minus 2, which is negative 1, and then we have negative T. And here you have 6 double negative, so 6 plus 1 is 7, and then negative T. All right, now what else do we know? We know, I can keep going back to this diagram here so you can see. We know that line, RP, is perpendicular to the direction vector M. So if we have these two vectors which are perpendicular to each other, we can use the dot product and set it equal to 0. So let's do that. So our direction vector M dot RP is going to be equal to 0. Now the direction vector M is right here, right, in our vector form, which is 0, 1, 1, dot, and here's RP, so you have minus 2, minus 1 minus T, and 7 minus T. And that's going to be 0. And this is going to give me a chance to solve for what T needs to be. So we have 0, and then minus 1 minus T, and plus 7 minus T equals 0. This gives us, if you rearrange a little bit, 2T equals 6, so T equals 3. Since I know that T equals 3 now, I know what that point R actually is. Remember before I said R is this point here? I just didn't know what it was, but it was a point on the line that is closest to the point off the line. And now I know what it is, because it is 1. Sorry, 1. Then it was 2 plus T, where T is 3, so that's 5. And then minus 1 plus T, where T is 3, so that's 2. So that's the bonus. So what we've essentially done is figured out that in our current example, that this point R right here is 152. Now that I know what that point R is, I'm actually going to just do the work over here because we have a nice diagram. Now that we know what that point R is, all I need to do is figure out the magnitude of RP. So RP, okay, and if you remember, P was minus 1, 1, and 6. So RP, just take the difference in their coordinates and you get minus 2, minus 4, and 4. And therefore, the magnitude of RP is the square root of minus 2 squared plus minus 4 squared plus 4 squared, which gives you the square root of 36, or 6. So it's the same answer. I mean, it should be the same answer. Otherwise, it's not a very good method of doing it. But we had that bonus of being able to figure out what that closest point was on the line to the point off the line.